All right, guys. So, let's see. I've got some things on the board. If you want to put them in your notes, that'd be great. Don't do it until I get to it, so it's actually in context. Does that make sense? It's usually best to put, write things down as you're talking about them. Oh, let's see. What else? Oh, AI. Yeah. You'll see on the screen, and if you can't see it very well, feel free to pull it up on your own computer. You have access to the daily tracker. That's what this is. So if you want to have that up while we're working as well, that's fine. But yeah, do I use AI a lot? Kylene, do I use AI a lot? Yeah. Yeah. So sometimes, like for example, I'll be like this summer, I worked on a couple different cars and the tractor, but the Mercedes, it's a 95. It still runs. It runs good, so it's cool. But the air conditioning system wasn't working at all. So I actually ended up replacing the entire air conditioning system. Am I a full-time mechanic? No, I'm not up on 1995 Mercedes air conditioning system. So guess what I would do? I would ask Google, and the Google AI was very helpful. Did it always get things right? No. Okay. So AI often gets things right. Sometimes it gets close. Does that make sense? So a couple of times it's like, oh, you'll find this thing here, and you connect that. I'm like, no, that's not there. You have the wrong layout. And it's like, oh, thanks for clarifying. And then it would try again and either get it right or get closer. AI is only as good as certain limitations. One of those limitations is your prompt. Probably the most important limitation to AI is the quality of your prompt. In other words, how you are asking the question. If you are very broad, it will give you a very broad, non-specific answer. Is that fair? Okay. The second limitation is its source material. Is AI coming up with original thought? No. AI harvests humans' original thought from resources on the internet or otherwise available to it. Is that true? Yeah. Doesn't mean it's not super useful at times. So anyway, AI for quick research. This morning, I had a question in my mind. I was thinking about yesterday's lesson, which will be posted soonish, probably tonight. I was like, wait a minute. If these stars are very large, I'm thinking like dimensionally, like the diameter of them is very large, and they collapse. Won't a lot of that material, a lot of that matter, have to travel a long distance, a pretty good distance before it gets to the center? So as it's collapsing, it has to go a long way. So this green circle with the arrows pointing in is the star, and the green arrows is the motion of the matter heading towards the center of the star. It's got to cover some ground. Won't that take a while? Unless it's moving really fast. So I remember reading some of our resources yesterday, and it had words like it collapses in an instant, or it said like in a fraction of a second. Okay, did you read any of that stuff? Maybe not. Okay. So I asked the question to AI. I have not done anything to this little conversation I had with Google AI. I said, if a supermassive star collapse only takes an instant, is some of the collapsing matter approaching the speed of light? I was worried that maybe we were breaking physics, because it's generally not a good idea for a physics teacher to break physics. I'm like, are we getting close though? Yeah. says, yes, matter collapsing in a dying supermassive star reaches extreme speeds very close to the speed of light. As gravity pulls the massive core inward, the velocity of the falling material accelerates rapidly right before it forms a black hole. So if it's forming a black hole, the inner parts approach the speed of light. Approach, but don't like break it. Has anybody ever heard the speed of light referred to as the cosmic speed limit? Couple of you nerds? Yeah, all right, good. Yeah, it's often referred to as the cosmic speed limit. You can't go faster than the speed of light. Why? Because the closer you get an object to the speed of light, the more energy it takes to accelerate it. And the more the mass actually, like, this doesn't get bigger, but the whole E equals mc squared thing, if you want to get to the speed of light, the mass gets disproportionately larger, something like that. It's been a minute since I was in physics class, like in college. So I asked that one, and it gave me an answer that was not surprising, which is good. But then I asked it another question. I said, hey, another thought. Have you guys hopefully been having some of these questions too? These random, like, well, what about this? So mine was, well, how much of a supermassive star, when it explodes, how much of it is actually blasted into space versus how much of it is incorporated into the neutron star or resulting black hole? So I start reading this answer, and it's not a surprise again, yet. So here's what I was expecting. It gives it to me. It says in a typical, oh, we got a clue there, right? In a typical core collapse supernova, 80 to 90% of the material is blasted into space, while the remaining 10 to 20 forms the neutron star, or if it went to a black hole, the black hole. However, there's the however. For truly supermassive, there's some other things going on. So I'm going to go to the chart that it gave me. And when I say it gave me, what's this right here? What's this little button? It's a link to what? A website, which was its what? Source material. Good. So you can check those and make sure they're decent ones. Astronomy Stack Exchange, sure. Whatever that is. A couple others I checked was Science Magazine, peer-reviewed. Another one was Harvard University. Another one was, what was the other one? Harvard, there was Las Cumbres Observatory. Okay, that seems legit. Routers? No, that's just like a generic media platform, right? Media source. Harvard, Astronomy Stack, show all. You can ask it to show all, show less. Oh, there was more to it than that. Anyway, look at the sources. Make sure that they sound... Oh, there we go. Astronomy Magazine. Okay. So anyway, the chart. Here's the headings for the columns. So we have the initial star mass shown here. We have the amount of the material that was blasted out into space. We have the resulting core remnant, like how much of the material stayed behind in an actual solid like object. And then we have the remnant type. So the first one was not surprising to me. The 8 to 20 times mass of our star, our sun, remember yesterday you guys saw that, forms a neutron star, and about 10 to 20% is left behind. The rest is blasted off into space, becomes a nebula or something, right? I got dust and gas cloud. That sounds familiar, right? It was just yesterday we talked about this. The next one also does not seem particularly surprising to me. I was expecting this too. Okay, maybe a little less, depending. Blasted out, a little bit more kept as the black hole. Okay, that makes sense. More matter, more likely to become a black hole. All right. Then it got really interesting. I'm going to put both of these up. If it's between 140 and 260 times the mass of our sun, all of it is blown away. Nothing left. There's no core left. All of that material is converted into a cloud of dust and gas. No remnant. And then complete 180, completely flipped over. If it's over 260 times the mass of our sun, that massive star, when it explodes in a supernova, None of it escapes into space. All of it is absorbed by the black hole. That was surprising to me. These two complete, like, very much it's all or nothing scenarios, those were kind of surprising to me. Did anybody know that? I did not. I don't think I knew that. Yeah, but I didn't know that when those went supernova, nothing got away. Nothing gets away. And I guess if you think about it, it kind of makes sense. The biggest ones, the gravity is so strong. It's so strong that even that massive explosion, that massive supernova, none of the debris reached what speed that we talked about yesterday? What? Escape. What'd you say? You didn't say it? Did you say escape velocity? Oh, okay. Yeah. So these hypermassive ones, the one that all of it is absorbed as a black hole, none of it reached, during that explosion, none of it was able to reach escape velocity. It couldn't get going fast enough because the gravity was too strong. Okay? Whereas in this next category down, all of it, the explosion was strong enough, all of it was able to escape that gravity. There was nothing left. I thought it was kind of cool. Now, while I'm at it, kind of catching up from yesterday, just crossing our I's and dotting our T's, guys, occasionally I will say something that is wrong, a misspeak, or just flat out wrong. Yesterday, I was describing those, for a lesser star, so not one of these, one that doesn't go supernova, one like our star. I was describing how the outer layers, as it swells, the outer layers drift off. Yes? Does that sound familiar? That's true. However, I called that a nova. That's incorrect. So if you put that in your notes or if you locked it away in your brain, that is not what a nova is. It just forms a planetary nebula. Those outer layers do absolutely drift off. I mislabeled it. My apologies. We actually won't talk about novas anytime soon. Maybe later. Questions on that? I want to be clear. All right, we've got a slideshow today. Monday we did like some group activities. Yesterday it was mostly lecture style. Today we just got on my noggin, which sometimes the reliability there. We got reliability issues. Today we're doing a slideshow. We're going to go all the way to the beginning. First and fifth we made it to slide U, which is pretty darn good. We'll see how far we get. With your class, here's your question. I want you to think, what would we find where those guest stars were? Where the guest stars were, if we were to look in that region now, what would we find? That's the first question. What do you think we would find in the region where each guest star appeared and disappeared so quickly? Second question, could telescopes, if they could, how could telescopes help provide us with some data that we could use to support or refute our predictions? Do you think we would see anything like what they saw when they saw the guest stars? Would there be anything there? What do you think? Talk about it real quick. What's your name? What's your name? What's your name? What's your name? Owen. What's your last name? Richie. Did I teach an older sibling of yours?
don't have any old stuff.
All right, that's long enough. Long enough. All right, what do we think? Are we going to find something there? If we were to point a super powerful telescope there, what would we find? Hanson.
I said like a black hole maybe.
Okay. Yeah, so what we just looked at, right? The chart we just looked at, do some resulting black holes have some debris around them? Can that be? Is that allowed by the chart we looked at? Yeah, not the biggest ones, right? Because all of it we absorb, but the ones before that. Looking back at that chart, hold on, let's think about that for a second. Back at that chart that Google AI made for me. If it was this one, where 100% of the mass was absorbed, and you had a supermassive black hole, I'm trying to think, if all of that material was kept in the black hole, none of it was spat out, would any of those guest stars have been seen? Why not? There's nothing there to see. None of the matter was out of the black hole to be seen. If it's in the black hole, you can't see it, right? So so we can rule this out, right? None of those guest stars that we read about would have been the result of this. It couldn't be, because all the material is in the black hole. Yeah. When she gets back. No, he'll get back, then she'll go and come back, and then you can go. Okay? I mean, you just came back from lunch. You should have gone to the bathroom at lunch. All right. Could the guest stars have been a result of this category where 100% of the mass got blown off into space? Absolutely. But then what you just said about there might be a black hole there wouldn't be true. But if we go up to the, one more up? So if what you said is true, which is possible, one or all of them maybe could be this category, where it was a very massive, it kicked out the stuff, that's the guest star that we could see, and there's a resulting black hole. In fact, isn't any of these three possible? That one, or this one. The only one not possible would be this one. Does that make sense? Kind of, sort of, maybe? All right, cool. False color. So before I get to that, how many of y'all have a telescope at your house? You've never used it?
Only once, and I put it on.
Oh. You should. Okay. Guys, if you have one and you've never used it, ask someone to show you how to use it, or just Google how to use it. What do you say?
I have used it a couple of
Yeah?
times. I looked at Mars ones.
Okay.
Very cool.
Very neat.
It was kind of hard to see because it was one of those
Still blurry.
stronger ones,
Mhm.
but it was still more visible.
Okay. The extra conversation, I don't know what you're talking about. It's probably not this, is it? Okay. So he says he's got a telescope, not a super strong one or anything. Yeah, most of us, in your house. And also, he was saying the Mars was it blurry? So you could magnify it, but it's still kind of blurry. Unless you're at like an observatory high up where you're out of most of the atmosphere, or a good portion of it, you're not going to get a super crisp image. Okay. Like if you're in orbit, like you're at Hubble Space Telescope or something, I guess then you might get a pretty good shot of it. It's just really far away. So I want you to think these guest stars are really far away. They were so far away that before the star went supernova, it wasn't visible, was it? So do you think your telescope at home is going to be able to see anything? No, you ain't gonna see nothing. Because these supernovae were hundreds of years ago or over 1,000 years ago. A lot of cooling has taken place. Yes, it's not going to be. It already disappeared hundreds or thousands of years ago from your naked eye. So that's a lot to be asked from a relatively affordable, right, at-home telescope. So, is there any hope at all that we'd actually be able to see if there's anything left there? I got a couple of heads shaking no. I don't know. Oh, that. See, I do that, and then you're like, oh yeah. All right. So the next slide. Read that if you can. If you're back in the nosebleeds, you probably need to pull this up on your own computer. I'll read it for you. It says false color. Stop. What does that mean? False color. Go. Okay, it's colored by something. So, do you think this is what it would look like in real life to our eyes? No. It's false color. But I can see the colors. There's blues and reds. It doesn't look like that in real life with our eyes. Does that make sense? So how did we get this picture? Yeah, it's edited, all right. But guys, this was not a photograph like we think of it. This is the frequencies of light that were received in a specific range of wavelengths. What's this word? Okay, so this was an infrared camera. It pulls from a very specific range of wavelengths in the electromagnetic spectrum. Is this somewhat familiar to you guys?
Yeah.
Okay, so the shortest wavelengths in the EM spectrum are radio wave, or longest, excuse me, are radio waves. On the visible portion, red is the longest, violet's the shortest. Outside of the visible range, gamma is the shortest, right? Okay. So there's a infrared camera takes this. Now you can program your computer. Yours at home, maybe not. I don't know. It's a software thing, right? You can assign colors to a wavelength that aren't native to that wavelength. Does that make sense? In other words, if there's a certain wavelength in infrared that represents a certain color, because infrared's all about heat, right? Represent a certain heat. Then I could say, well, for this heat range, computer, show that in a picture in the color blue. And show this slightly longer wavelength in the color of red. Does that make sense? So that's how we have these. So normally you have infrared images. The bluer or brighter, whiter colors are hotter. And you can flip it on your computer. You can flip that assignment. But I'm seeing this. I'm thinking the whites and the blues are hotter, and the reds and the darker areas are cooler. Okay? Another one, by the way, this was guest star 185. So this was a supernova that we saw in 185. So almost 2,000 years ago. This image was not taken 2,000 years ago. This image was taken recently. Doesn't have the date here, but I would guess probably within the last 20 years or so, yes.
Is it because like the light finally got to us?
So the light's getting to us, yeah. And it takes a long time. It travels at the speed of light.
Yeah.
So all of these wavelengths of light travel at the speed of light. It's the same. This is just the amount of energy carried in that wavelength. Okay? So it's getting to us a long time later, and it's still showing a lot of heat. Still showing a lot of heat. Remember, when they first saw it in 185, it was a long time ago that it actually happened, because it took that long for the light to get to us, right? But there's still enough heat there that they can make an image for us to look at it. Is there stuff there? Yeah. You're seeing the stuff. All of this light, it's infrared radiation being emitted by the particles, by the matter that blew off of that star. This is a dust and gas cloud. Are you on your phone? Yeah. Okay. Awesome. I love being proved wrong. I suspect. Thank you. All right. Here's another one. What bands, what range of frequencies is this taken in? Go ahead. Nope. Read it. What's this at? X-ray. So we were in infrared. This image was taken way over here in X-ray. Remnants of guest star 1006. So this is just over 1,000 years old, or after we saw it happen. And we've got a bunch of remnants here, a glob of dust and gas. I wonder how far across this is. You can see in the background, or maybe inside of their little specks. I wonder if those are stars behind or just like in the foreground in the image. I'm not sure. You guys ever just wonder about things when you're looking at images? I bet you could look that up. If just maybe one of you wanted to look it up, how large or like how big across is the nebula resulting from guest star 1006? Like, I'm guessing it's measured in the light years. I don't know. Yes.
It looks like there's like a big ball of water.
Oh yeah, it looks kind of like a bubble. Yeah. The next one even more so, with that blue like aura around it.
60 to 65 light years.
60 to 60. I'm glad you found it. So this last one, from end to end, it's between 60 and 65 light years across. That's immense. Yes. Yeah. Yeah, because he's gone. So once he gets back, unless it's... No, he hadn't been going there. If you got to go, go.
No, I can wait.
All right. This is from 1572. So this is the one that Tycho from Denmark, right, saw.
Yes.
Also in the X-ray. And then they reassign, they assign colors to those frequencies so we can kind of imagine what it looks like.
I think that one's smaller because you can see the stars better. It's bigger.
Maybe, I don't know. You could look it up. 1604. This one reminds me, you're just looking at it, this one reminds me of what, kind of similar to what a red blood cell looks like under a microscope. Except for the blue around it. And then finally, we're looking at our own star. And what a difference, right? This one's true color. It's close enough, bright enough. We don't need to do X-ray if we don't want to. We can just regular light. Note, however, that this one was taken aboard the ISS. So this is outside of our atmosphere, no interference from atmospheric gases. This one is false color. This is UV. This one's in UV, ultraviolet. So that we're looking at a false color of the stuff that burns your skin, right? That's only one type of UV, though, right? There's different wavelengths of even UV. What's the one that the nail polish dryer curer thing? Is it UVB or UV? Huh? UV what?
UVL.
L? Okay.
UV light.
I don't know any of that stuff. All right, we got a picture of all the ones that we just went over. Turn and talk. So you guys are going to discuss this one next. What's an inference? Okay, what educated guesses, what inferences can you make? Why are we talking? You're going to talk. You're not talking yet. I'm telling you. Okay. can you make about the differences between stable stars like our sun and the guest stars that we've looked at? And also, what can that tell us about what happened to the matter that made up the guest star? Go. And I'll go back to the image so you can see it. Why are you asking him about that? That is not what you're supposed to be talking about. You're supposed to be talking about this. You're getting in a habit. I'm going to come down on you hard. Every year, there's got to be an example set. Do you want to be the example? Okay. What?
Like, what's this red dot in, like, during the supernova? What is that, like the remnants of it, or is that like when the black hole is starting?
I don't know. Is this an actual like image taken with some sort of instrumentation, or is it an artist's rendering?
I'm not really sure.
So be careful with those. Sometimes they put up artist rendering. Now, if it's an actual image, I don't know. That's glowing pretty hot there. I don't know. I don't know. Don't make me lie to you. If that was taken during or just after the explosion, very, very recent, then that neutron star might still be emitting some light. Absolutely. Yep. Okay.
How there was that chart where it was however big the star
Yep.
was whenever it
Yep.
exploded? Where would our sun be?
Not on it.
Not like
It's less massive than. So the lightest on that was 8 times more massive. Because ours won't go supernova. What? You're doing a discussion. You might take notes during, like, whenever I'm talking. Yeah, when I'm talking to you, if you get something new, right?
I did not realize how long the hike was.
You're talking about things that are off topic. Do I want to make an example out of you?
No, our sun's on fire, and our sun is not dead. It's yeah. Oh yeah, those. I think that. Wait, is our sun smaller than those? Is our sun smaller than the ones that have?
These are massive clouds, expansive clouds of dust and gas. Our sun would be a speck inside that.
They're a lot bigger than our sun. Yeah, a lot bigger than their gas.
All right, bring it back. Bring it back. So again, the question was, what can you infer from the pictures? Based on the pictures, what can you tell the differences between a guest star and a stable star like our sun? Go, give me something.
The stable star is a lot brighter.
It's a lot brighter. Why?
Because it's like stable, and the other stars are making it collapse and into
They already collapsed in. They already exploded out.
they explode. So they're not bright.
Still emitting light through what process? You don't remember what stars do to emit light? What? Nuclear fusion. Guys, shh. So you said the stable star is brighter. Yeah, they're brighter because they're actively going through nuclear fusion. They're releasing light and energy, another energy, from the nuclear fusion. So they're bright. This thing blew up a long time ago. Long, long time ago, it stopped emitting light in the normal fashion. There would be an afterglow, perhaps, right? And we see some of that with the infrared and in the X-ray. What else? Go.
It looks like the guest star, like 106 and 1604, like it looks like they're
Extra conversation over there is probably not paying attention to this. Go ahead.
Like they're kind of like staying kind of together almost.
All the debris?
Yeah, it's kind of like staying together.
It looks like there's a boundary, doesn't it? So, the cloud is expansive. It's very large. It blew out, but it still kind of seems like it's got some boundaries. You can easily, it's got defining characteristics. But we're talking about tens of light years across. These things are huge. What do you got?
It just kind of seems like the guest stars are a lot bigger than our sun.
These are a lot bigger than our star for two reasons. They started as bigger stars, and they exploded. So the material that was that star is now scattered over an incredibly large area. I'm going to put this in perspective. If we're talking about tens of light years across that these clouds are, well, how big is a star? All right. The distance between our sun and our nearest stellar neighbor, which is what, Proxima Centauri, is 4.2 or 4.3 light years. In other words, our solar system and our nearest neighboring solar system would easily fit inside one of those. He goes, what? Yeah, I'll say it again. Our solar system, our whole solar system, and our neighboring solar system, our nearest neighbor, would easily fit inside of one of those clouds. You could fit them both on the same side. Does that make sense?
Yeah.
Barely, right? It's kind of mind-boggling. It's huge. Remember what we said, though. We think that these clouds of remnants will eventually recondense into perhaps new systems, right? They're big. Light bulbs. Oh, you have a question? Okay. Anybody want to share anything else before I move on? Okay. It's nuts, right? Scale is crazy. Was this class yesterday that we said the galaxy, our galaxy, from one end to the other is 100,000 light years across? Was that not your class? Okay. You can fact check me on that because sometimes I get zero in the wrong spot. Was it 100,000 light years across? What? A light year is the distance that light can travel in 1 year. The speed of light is 186,000 miles per second. I'll say that one again. The speed of light is 186,000 miles per second. In other words, if you think about the Earth's circumference, it's about 25,000 miles, right? So divide that 186,000 miles per second by the 25,000 miles. Light is so fast it could go around the Earth just over 7 times in 1 second. That's fast. So what's a light year? That speed, 186,000 miles per second, times 60 seconds in a minute, times 60 seconds in an hour, times 365 days worth, right? So times 24 times 365. It's a long way. Okay. Light bulbs. Oh, you have a question?
What's like the boundary of the galaxy?
Is there a strict boundary to a galaxy? So depends on the type. Ours is a spiral arm galaxy. And so that outermost spiral, which is just a band of stars and star systems, the ones on the very edge, I guess that's the boundary. That's the end of it. but could that expand and contract slightly as they orbit the galactic center? I'm sure there's a little bit of, just like the Earth wobbles as it spins, I'm sure the galaxy has some wobble in its spin too. If that kind of sort of answers your question. That might be a Googleable question too. Probably no better than finding somebody that knows more about it than I do. Light bulbs. Were you here when we talked about light bulbs last time? No? You're just getting a little different piece of the class every time you come in here. Yeah. So, what's your favorite light in this room? Do you prefer this light panel, or do you prefer that light panel? Show of hands, who prefers this one? Who prefers that one? Why? Somebody tell me why you prefer one over the other. Go.
That one has a warmer light.
Oh, a warmer light, she says. More yellowish, and this one's bright white. What if I were to be more specific? How about this? Which of those two would be your favorite when working in the kitchen? Some of you still would prefer the yellow one? If you said this one, why did you say the whiter light? Not you. Somebody else. Go. It's a little bright. It's a cleaner light. It's like if you're doing precision work, you want to have maximum illumination, right? Who said warmer? Was that you? So that light's a little warmer, we think, right? Would you prefer that to this one, let's say at 8 p.m. in your living room? I had somebody earlier say this one gives them headaches. It's too intense.
Okay, girls, what about which one for putting on makeup?
That one.
Good question. He said which one would for putting on makeup, the brighter white one. Yeah. If I'm out in my garage and I'm trying to see, working on the car, I'll be turning on my white bright LED fake fluorescence, the tube style. I don't know, why do they do that? It's like we're familiar with fluorescent style light bulbs, so we're gonna fashion an LED light that looks like a fluorescent light. It's so silly. The ones that are the bright whites in here are replaced. The ones that are more like the yellow are actually still fluorescent light bulbs that have not been replaced yet. They're transitioning all of the lights in the building to LEDs. Yep. So this one is an LED. That one over there are traditional fluorescent light bulbs. Do you guys know the difference? So this one is a light emitting diode. It is like over my head. I haven't done any research on how they really work. Okay. But are we almost out of time or something? They're putting their stuff away already. But that one has a gas in the tube. And the electricity is run through the tube, and the electricity excites the one over there. It excites the gas. And depending on the gas, it will put off a certain set of frequencies in the visible spectrum that gives us the color, the warmth that you're talking about. Absolutely. Anybody go light bulb shopping? If you look at the package, they actually have like a temperature range, temperature of the light. Yeah. Absolutely. What?
When they go out.
Eventually they'll go out. The gas will still be if they leak out, then yeah.
You notice the end will start to turn black.
Yeah. Chart up. What?
I have a question from earlier.
Yep.
The galaxy is like infinite. How's it still growing?
The galaxy is not infinite.
I mean,
Oh, the universe. So it's still expanding. It's not infinite. There is an end to it, but that end is expanding. So a lot of people refer to it as infinite because it's still expanding.
How many of you all think there's life out there somewhere? Nobody thinks we're it.
We're it. There's no intelligent life anywhere. Yeah. Oh, you'd have to look that one up. Hey, I guess this is the last thing before we run out of time. She says, how fast is the universe expanding? So actually, a long time ago, they thought, it burst into existence, right? Big Bang. and it expands out to a certain point, and then it slows down and comes back. No, that's wrong. It's actually still accelerating.
So that means that eventually everything will get so far apart.
All right, so we were saying that depending on the situation, we might like brighter white lights. We might like warmer yellowish lights. Okay, whatever. What's that got to do with anything? Well, I keep doing that. When you run that light through a prism, the light gets separated out into its what?
Rainbow.
Into the different colors of the rainbow. Yeah, all those different colors by wavelength, right? The wavelength of the light determines what it looks like, or doesn't look like at all if we're talking about the spectrum outside of the visible part to us. Yes? Okay. Continuing on with the slideshow, though, because I want to give you maximum time for study before the quiz tomorrow. I'll go over it. Oh, did you hear a rumor?
I've heard many rumors.
Many rumors. Well, there's only one rumor. It is not a rumor. It's a quiz, 5-question quiz tomorrow. Shh, shh, ha, shh. 5-question quiz tomorrow over star composition and temperature. You know, being able to understand the difference between guest star composition temperature and the stable star composition and temperature. Okay. Yeah, it really should be pretty easy, especially since we're like going over it more in depth today. Yes. What if you fail? Then you fail. If you fail, you fail. If you pass, you pass. Okay. Was that a trick question? Okay. Okay. So check it out. You've seen that image before, right? Okay, cool. So moving on. You have a light source. So if it's just a regular incandescent light bulb, cool, whatever. And if you click on that and go to the web page, you can actually manipulate it a little bit. So if you put it over by the light bulb, it's going to show you on the spectrometer, it's going to show you all the colors because you're observing all the colors directly. There's nothing in the way. Does that make sense? So you get to see all the beautiful colors. But if you position it over here, now the light has to pass through this plastic bag looking thing that's supposed to represent a gas cloud. I don't come up with the animation. Does that look like a gas cloud or a plastic bag thing? Yeah, to me. Anyway, it's supposed to be a gas cloud, okay? So that light that had all those colors goes through there and the gas absorbs certain wavelengths. Do you see the spots that are missing? Okay, those are called absorption lines. So the gas is absorbing certain wavelengths depending on the makeup of that gas. In other words, what elements are in there. Okay, each element will cause certain specific absorption lines. It's like a signature. Does that make sense? Okay, an elemental signature will show up on your spectrometer. Okay, so moving on to the next slide. So here's just an illustration showing you got a light source, you're passing it through a canister of gas. The other side, you're going to be missing certain color wavelengths. So the question is here, if the gas inside the cylinder absorbs yellow light, what do you think the spectrum coming out the other side would be looking like or missing?
Missing yellow.
Be missing yellow, right? If it, would it be missing all the yellow? It depends on how much gas is there that's absorbing which wavelengths of yellow. Is there only one wavelength of yellow? There's a range that we would describe as yellow, but different shades, right, based on the wavelength. Okay, cool. So we go to the next slide, and it's going to show us what's missing.
Black. Oh wait, no, yellow.
The yellow's missing. It's just nothing there, right? Black means there's nothing there. All right, cool. So the dark band we see in the spectrum corresponds to the color that was absorbed. Such a dark band in the spectrum is called an absorption line, as I just explained. So if that makes perfect sense to you and you think you got it stuck in your noggin, great. Otherwise, that might be a vocab term for you. It's up to you. Absorption line is a dark band in the spectrum caused because something in between the light source and you absorbed some of those wavelengths. Every element absorbs a unique set of wavelengths of light. So you can analyze that and say, oh, well, these wavelengths are missing. That means this element must be present. And we're going to look at a couple. Scientists can identify the composition of any gas from the absorption lines in the spectrum it produces. So here we have oxygen and hydrogen, what they would look like as far as their absorption lines. You see there's several lines actually for oxygen, aren't there? Some dimmer than others. Hydrogen has 4 pretty bold absorption lines. One over here in the red, one in like the light blue, and then a couple over toward the violet. Think time. What would, and think, you're supposed to, individual think time, so think to yourself. What would the absorption spectrum for sample A look like if sample A was a mix of hydrogen and oxygen? What would a sample spectrograph look like if it were a mix of oxygen and hydrogen? What do you got? It'd be down there? You're saying, oh, the hydrogen lines wouldn't show up? Why not? A little bit? You think oxygen is better than hydrogen? You got a problem with hydrogen personally? Like, what did it do to you? You drink it every day. And what's in water?
H2O.
Both of these. You drink these together, guys. Why you got something against hydrogen, but you're okay with oxygen? They're best friends. Right? Oxygen and hydrogen love each other. H2O. So there's 2 atoms of hydrogen, 1 atom of oxygen in a molecule of water, yes? So what do you think?
Obviously, if you took the oxygen out of water, would it be hydrogen?
Yeah, if you stripped the oxygen atom off of water, you'd be left with hydrogen, right? You'd be separating. We're going to do that this year.
Are they gonna look like a different color of water?
No, it wouldn't be water anymore. You'd have 2 gases.
You add like another element to it, would the water look different?
If it was like a mixture, yeah, it would look different. If you were trying to add another atom to the molecule, well, you'd end up with a different molecule, wouldn't you? Wouldn't be water anymore. Okay, anyway, what would this spectrograph look like? Go. You'd like transcribe them down here, right? So this little faint line would be here, the same spot, down in here. So if you were just to like bring this over that one, and both of them would show up, right? So down here, if the sample A had both of those in it, you'd have an absorption line here from the hydrogen, you'd have an absorption line here from oxygen, and so forth. They would both be in sample A. Question or comment? Go ahead.
Would they kind of equalize a little bit? They're still lines, but they're very...
Okay. So yeah, depending on what the mix is, they might be fainter, right? If the percentage of them was different, yeah, you could have like this really bold absorption line might be fainter if there's in the mix there's less of the hydrogen. Okay, cool. All right, moving on. We're good to move on. All right. So there you go. Take the 2, put them together. Does this one look a little different than that one? A little cleaner, a little thinner maybe. So yeah, they might change a little bit. This one, I don't know. This might be a little fainter. So I kind of like what you had said, yeah. All right. Make predictions. Stable stars produce light of all wavelengths. As this light goes through the gas around the outside of the star, some of it gets absorbed depending on the elements that make up the gas. So the star is emitting the light from where? From inside, right? Those packets of light energy, those photons literally go like a pinball machine. Ping, 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 ping. They got to bounce around for actually a pretty long time. You'd have to look it up. I can't remember, but it's a surprisingly long amount of time that those packets of light energy, those photons of light, are bouncing around inside the star before they find their way to the surface, where finally they're free to go. Does that make sense? So if it's actually being emitted from the inside, those gases on the outside of the star, the light has to pass through that. Yes? So some of those wavelengths of light are going to be absorbed by those gases. Okay? So you end up with light from our sun, for example, with absorption lines that will be a dead giveaway to what the sun is made of. So it's showing you here, hey, here, remember we just looked at it. Here's hydrogen's absorption lines. 1, 2, 3, 4. We see them in the light from the sun. Questions? Cool. How would it support the claim that the hydrogen is one of the elements that make up the sun? Because the signature is there. Moving on. We've got our spectrograph up here with the bands that we've been looking at, the absorption lines. And now they just kind of like turned it on its side almost. And the y-axis here is the brightness. Notice which color is brighter in this sample of starlight. Is it the red or the blue? The blue is much brighter. What would we say about the temperature of this star? On the cooler side or on the hotter side? Blue is hot. I told you, don't get it twisted. Oh, it's red hot. No, blue hot is hotter. Remember we talked about, did we talk in this class about a gas stove? When you're adjusting the temperature, if it's actually adjusted cooler, it's going to be more like orange and red flames. If you dial it in and get it hotter, it's going to be more like blue or white flames, right? Blowtorch. Anybody ever use a blowtorch or see a video of somebody using a blowtorch? When they first light it, it's like, and then they dial it down, it goes, right? And it gets hotter. So it goes from a fuzzy reddish orange flame. They dial it down, get it nice hot flame or a hot blowtorch, and it's like blue, right? So a star that is hotter is going to be more blue, brighter on the blue side. A star that is cooler is going to be brighter on the red side. Yes. Yeah, I guess. Yeah, because all of them together make up white light. So when you separate white light out, is there white up there? No, white is not one of these, is it? So it would be a certain combination of those. If it looks like just a white star, you're probably pretty even. So you're probably kind of in the middle on the temperature. Does that make sense? Okay. The absorption lines, though. See how they dip? They dip because there's less brightness at that wavelength. Well, why? Why is there less brightness at that wavelength? Because the gas absorbed that wavelength. Absolutely. You guys are on it. You guys are on it. I love it. All right. Connect to prior experiences. Empirical evidence from spectral analysis has helped scientists determine that our sun is made about 98%, at least over. It says over 98% hydrogen and helium. Vast, vast, vast majority. In 7 billion years from now, would that be true? No, you'd have a much lower percentage of hydrogen. You'd start seeing things like lithium show up, some carbon, certainly a lot more helium. With your class, how does the atomic mass of helium and hydrogen compare to the other elements? It is much. They are much what than the rest of the elements? Much smaller. Okay, I like the word smaller. What else?
Minute.
Less massive. They are the two least massive elements on the periodic table. Hydrogen's only got a proton in its nucleus. That's all it's got. One is its atomic mass. Some of the isotope, most common isotope of our other version of hydrogen just has one neutron, so atomic mass 2. But the vast majority of them just have one proton. That's why the average atomic mass is barely over 1, because the vast majority of them just have a proton. Does that make sense? Whereas over here, helium, like, it's dead on 4. It's got 2 protons and it's got 2 neutrons, so atomic mass 4. Is this ringing bells from middle school science, maybe, hopefully? Did you guys learn that stuff? How to read a periodic table? You didn't?
6th grade.
6th grade? So 6th grade, so a couple years ago, 3 years ago, you've forgotten by now. If you did learn, you forgot. You just never learned. You're sure.
Yes.
I didn't have 6th grade science.
You didn't have science?
Well, not
What do you mean you didn't have science? Who was your teacher? They both got fired?
No, we got cut. We got cut.
Yeah, so a lot of teachers just they didn't get fired. They basically got laid off, right? So yeah, last year into this year, it was like, whoa, we have to do how many cuts? And it was pretty steep. Our science department here, the reason I have 31 students in this class and 32 students in my fourth period, and the reason I don't have a planning period, so I have another extra class. The reason I had to drop military science program, because I needed an extra class. Why? Because when Mr. Farrar retired, that was like good timing, because if he hadn't retired, who would have been let go? We had to cut a teacher. It wouldn't have been me. I'm tenured. They still could have cut me, but they would. Mr. Farrar was the old guy that worked in this room. Mr. Farrar. No, he retired though. He was like 75 years old. He's the GOAT. So no, Mr. Poe, who's really cool, and yeah, he seems really nice, really cool. So anyway, he's the youngest guy. He's not tenured yet. He probably would have gotten said, "There's the door," which would have sucked. What? Sure, passes right there. Let's get back into it. We got to keep moving. With your partner, what patterns, guys? Look at the patterns in the spectra. Okay, I'm gonna explain this graphic for you, so hopefully you understand. And then you can look for patterns with somebody next to you. Each row is a different star. The names of the stars are over here. The temperature of the stars is over here. It's got a note for you. Hey, our star is right here, kind of in the middle-ish. The wavelengths of light are here. Of course, you can see the colors. And we have some absorption bands pointed out for you. Now, go ahead with a partner and share, what patterns do you notice? That's always fun when you take a drink from your coffee and you find a fly in it. He probably pooped in here. Died and pooped. Yes. When she gets back. Unless it's an emergency, I don't need an accident here. A little something right here. Oh. Hey, every once in a while, I'll still get a pimple. They suck. Mine are usually like under the skin, the ones that are just kind of painful and like uncomfortable. All right. That's probably long enough. Most of you otherwise are probably talking about who you're wanting to date or who you think's, whatever, super smart and not smart and what your favorite teachers was. All right. Shh. Somebody, what pattern did you notice? Go.
I noticed that in the light blue area, there's like a big, just like black, like missing piece.
Right here?
In the light blue area, it's like goes down.
There?
Yeah, I feel like on most of the stars.
A missing piece that we call an absorption line. So these stars, all of these stars have an absorption line about the same spot, right? So they probably have, all of them, hydrogen. That's the signature of hydrogen. Yes.
The bottom one on the yellow, that's also one.
Right here?
Yeah.
And what do we notice about these that's different from the rest of them? It's darker. It's much darker. Absolutely. So these stars down here, do we think maybe have more hydrogen? I don't know what that means. I have to think about it. What?
None of them have any purple at all.
The violet way over here. So the violet light is coming through, and there doesn't appear to be any absorption lines in there. Is that what you're saying?
I'm kind of seeing there is a line where it's dark, or maybe it's just.
Oh, right here.
Yeah.
If that's an absorption line, it must be something that they don't have labeled. They don't have this is lithium or whatever. Okay. But yeah, you guys can see that they're pointing to them. Now they point to this hydrogen one. I don't really see it until way down here. Do you see it right down there? This hydrogen one, it not there, and then all of a sudden it's here again. And the helium one is darkest here. Anyway, you guys can see the those details. Anybody, something else? A couple other classes saw another kind of detail. Huh? There's what, red right here? Yeah, I see that too. But it must not be hydrogen or helium, or they probably would have had it labeled. Yes. How about if we look at the red? Is the red darker or brighter at the top or the bottom? Darker at the top, brighter at the bottom. How about the blue? Brighter at the top or brighter at the bottom? Brighter at the top, darker at the bottom. Okay, guys, look at the temperatures. Is that, do you think, maybe influencing how bright that color light is? Absolutely. We said the hotter stars will have a brighter blue, yes? So more intense blue light. Well, as we go up the temperature, what do we see? Yes. And if it's a cooler star, it would be putting off more red light. What do we see? Brighter down for the cooler star. So totally confirms kind of what we were thinking. Love it. Did anybody have anything else? Okay. Poll for you. I'll ask the question, I'll read the things, and I'll say which one you want. How do you think the type of matter that makes up guest stars will compare to stable stars? So, in other words, we're talking about the elements that are present there. How do you think they'll compare? Will it be almost the same, or will they be different? The elements present with a guest star versus a stable star. Who says they'll be about the same? Who says they'll be very different? Yeah. So, can somebody explain to me why? Why will the guest stars be very different when we're talking about what elements are there than the stable stars? Go.
Because the guest stars are producing different elements because they just explode from the collapse.
Not are producing, we're producing, right? So the guest stars went through their life cycle and exploded. So while they were going through the life cycle, long ago they did the whole hydrogen to helium fusion. They since then kept going down. Some of them went all the way to iron, right, before they exploded. So you're going to see things like calcium. You're going to see things like silicon and oxygen. Whereas the stable stars are still in the, hey, I'm taking hydrogen and fusing it into helium stage. That's all you're really going to see is hydrogen and helium in a star like ours, right? Does that make sense? Cool. Does that make sense? Yes, no, maybe? Okay. Next one. How do you think the temperature of this matter will compare? So the same matter, the same elements, the dust and gas that's out there, how do you think the temperature will compare? A is guest stars are colder. B is guest stars are hotter than the stable stars. And C says they're about the same. Who says the guest star is colder than the stable star? Okay. 1, 2, 3, 4, 5, 6. Guest stars are hotter than the stable stars. C, guest stars and stable stars are in the same temperature range. Nobody thinks that? Okay. Well, yeah, same? You think the same? Okay. So if we go to our Google Classroom real quick, go to 7th period, you'll see a new resource today. Oh, 6th, my bad. I've done that twice today where I was like, oh, we're in this period. They're like, no, you're not. Go to that new resource. Let's do handout. And like the first thing, the first sentence or whatever, what does that say? Yeah, the temperature. Each of the 4 guest stars below, temperature shown exceeded a million degrees Celsius. Now, is this like thousands of years after the supernova? No, this is like soon after, right? Like it happened, it's ridiculously hot. Do things cool down in space? Do they cool down as effectively in space as if they were like in our atmosphere or in the water or something? No. Why not? Why not? What do you think? So let me put it to you this way. I'm going to ask you this question. If I took a hunk of metal, okay, let's say I have this 3-hole punch, and I heat it up to almost to the point where the metal will start to melt. Okay, it's like red hot. It's like glowing red hot, and I do that in orbit. It's up in space. Okay, the temperature will start to drop. Yes, but think about why. If it's here on Earth, what is touching it? The elements in the air. Yeah, so the things in the air. Have you guys heard of convection? Please tell me, right? So the heat will actually warm up the air around it, and then that warmed air will rise off of it, yes? And then cooler air will come up and touch it and get heated and rise off of it. So it will cool because of its interaction with the molecules in the air, yes? Can it interact with molecules in space? Not unless something came over and literally touched it. Speaking of touching it, if I touch it right now, this thing feels cold. It's room temperature, but it feels cold because my heat is doing what? It's moving into the metal. Again, if it's in space by itself, is it able to conduct the heat away? No. So it can't convect the heat away. It can't conduct the heat away. The only way it can cool off is through what? It's in space. Radiation. It can only radiate the heat away. What kind of radiation is it going to be taking that heat energy away? Primarily, it's going to be what? Remember we talked about infrared radiation being like the stuff, that's the radiation you feel on your skin when you go outside the sun. That warmth from the sun, that's the infrared. So if I put this in space, it would actually hold on to the heat probably longer than it would if it was sitting right here. Okay? So that debris from the supernova, it's going to take a while to cool down. It is going to take a while to cool down. So anyway, 1,000,000 degrees Celsius, yeah, a little hot. Whereas if we look at our chart of stable stars again, and we look at the temperature range, we're what, 5,300 degrees here Fahrenheit up to, and they got Kelvin here. The other one was Fahrenheit and Celsius. So I've got two different charts. I got this one, which is Fahrenheit and Kelvin, and the other one is Fahrenheit and Celsius. So you've got things to choose from. But you can see up to almost 79,000 degrees Fahrenheit down to 5,300 degrees Fahrenheit. Way cooler than those guest stars. Okay. Here we go with a partner. Compare the composition and temperature of guest stars to stable stars. So do that with a partner. You're going to be using this document. Okay? Give you like a couple minutes. With a partner, compare and contrast composition and temperature of stable and guest stars. Yes?
What are the words around where you live? Because I wanted to add it in my notes.
Here?
Like the two outside of it.
Oh, radio waves?
Radio waves?
Yep. Radio waves are the longest wavelength of light. Microwave are shortwave radio waves, so they're the next shorter. IR is infrared. You've got visible spectrum, ultraviolet, X-rays, and then the shortest is gamma. Gamma rays. Gamma. I wasn't saying that your gamma was short, like your gam, or whatever you call your grandma. What do you call your grandma? Mama? You call your grandma what? Mama? I've heard people call grandpas papaw. So mama and papaw. What?
Can you repeat the question?
Yes, the question was with a partner. Compare and contrast the temperature and composition of stable stars with guest stars. Yes. Yep.
So, let's say we don't know what to do on the test.
The question I just asked you, if you get a decent understanding of that one question, you will do pretty well on the quiz. And if you were kind of paying attention for the rest of the time, yes.
I wanted to ask it. You said which one of these are the guest stars?
The four, 1, 2, 3, and then the fourth above it. Those are guest stars. All four of those. This is again, but without the writing here, and then all the way at the bottom, those are the stable stars.
So can you explain a little bit
These ones on here, the stable stars. And then these ones are
No, down. There you go. Those are the stable stars. Yep. All right. Let me go up here so I get everybody right. All right. Shh. So to clarify again, it says the 4 guest stars shown below: 1, 2, 3, and 4. And then it has, I think, the same thing, but without the writing here, right? So these are also the same guest stars if you read them. And then the last thing is a list of stable stars. Okay? Yes.
What makes the guest stars hotter?
What makes them hotter? Oh, okay. So think about what just happened to them. They were supermassive stars that just collapsed and exploded. That was a lot of energy, and a lot of it's in the form of heat. Good question. Did you guys have another question to go with that? Please ask. Okay. Yes.
What process makes the explosion? Is it like a rock?
What process makes the what?
Makes it explode. Like I know it collapses.
So, yeah. What causes the collapse is, so as the star is still in living mode, right? While it's still doing nuclear fusion, it's putting energy out. Yes. That outward energy is able to counteract the gravity pulling it this way. So what you have is force out from the nuclear fusion, the energy pushing outward from the nuclear fusion, and then the green arrows are gravity pulling in. They're in balance while the star is stable. As soon as there's not enough energy out from nuclear fusion anymore because it's done, then it's going to die. Hello. It's working. Up to the office. She's getting checked out. Okay. All right. Bye. All right. Did that answer your question? It's a balance act. So as soon as that nuclear fusion stops when they hit iron, because there's less energy coming out of that reaction than they have to put in to make it happen, then basically you're losing some of these. They're getting weaker.
I'm asking, like, is there a specific chemical thing that happens that makes it go out more? Because if it explodes, it goes out, right?
Oh, yeah. So think about it. So it's going to collapse. It's going to collapse in, okay? And then there's like a rebound. That rebound, so it collapses in and explodes.
So it implodes and then excess.
Yep. But not always. So, guys, yesterday we looked at the different ways, the chart, right? So the very bottom one, the supermassives, when it collapses in, the gravity is too strong for there to be a rebound. Imagine taking a basketball and dropping it, and it just sticks to the floor. That doesn't make sense, right? You expect it to rebound. But if the gravity is too strong, it can't rebound. It can't bounce back. Whereas if you have a less massive, then you're going to have some rebound. So a certain percentage of that material is going to be able to get out. Okay? Or if in the other case, there was the one that the explosion is strong enough and the gravity can't hold on to any of it. Did that answer your question?
Yeah.
Okay, good. All right, moving on. Do we have good discussions here?
Yeah.
Okay. What we've got, we didn't talk about it. Did everybody see the element key? Did everybody see the key? Okay. And then so you're looking for the colors, and it says right here, it kind of does the work for you. It says, hey, main features of this spectrograph, hey, we've got no hydrogen. We're not seeing any signs of hydrogen. This one says we've got strong signs of hydrogen. This one's got weak hydrogen, strong helium. This one has no helium or hydrogen. So I want you to think about which of these four do you think was the smallest star to explode out of these four? Which is the smallest, do you think? No helium, no hydrogen? I don't know. I'm not explaining it well enough. It's not really important for this class. It'd probably be a full-on physics course thing.
Whenever a star explodes, like the bigger they are, the more hydrogen they eat, so there's a lot of hydrogen left over.
Oh, you're thinking that there would actually be more left over if it was bigger? I'm thinking that way. It doesn't mean I'm right. That is not part of the curriculum. Okay? Do you have something else to say? Because you seem like you were understanding it pretty well. That detail is not. Okay. You're not going to be one of those students that's like, well, if it's not on the quiz, I don't need to know it. I don't. Okay. Okay. All right. And then down here, we've got evidence for just the light elements, hydrogen and helium. Yeah, we did. All right. Last slide on the slideshow. I will do more research into that and see if my thinking was right or wrong and try to explain it to you, okay? I owe you guys that. Remind me, okay? All right. Stable stars are made of mostly what and what? And their blank vary across a certain range. I think temperature. I think they're looking for temperature there because it was like 5,000 all the way up to 70-something thousand degrees. Hydrogen and helium are the two lowest what elements? Lowest mass elements. Guest star remnants are much blank than compared to the temperature of stable stars. Much hotter. Guest star remnants contain blank than hydrogen and helium, and in some cases no hydrogen and helium. Heavier elements. Very good. Much contain, I guess it would say contain more heavy elements. Something like that. As the last, I've got this, guys. I think you're in pretty good shape. Use the slideshow to help you go through, and you can fill out this worksheet. It's like a review sheet. Yeah, it's to help you kind of refresh what we just went over for the past 2 days. All right? I had the option to give this to you while we went through it. I chose to give it to you at the end. So if you need to go back in, if you didn't remember it, it gives you a second crack at it. Does that make sense? I mean, that's how I rationalized it. So again, the quiz tomorrow, you need to know, guys, you need to know the difference between a guest star and a stable star's temperature and composition. We just talked about that. So which is hotter, a guest star or a stable star? Guest star. Cool, you got that piece, right, broadly. And then what about composition? What's the difference? Heavier elements would be present. Okay, good. Did I miss anybody? A whole bunch. Is the pass there? Well, you'd probably want to have it done by tomorrow because the quiz is tomorrow, right? I want you to work on it right now. But you only have a few minutes left. But you work on it now, yes. I cannot hear you. Did somebody ask me a question? No? Jack, what are you doing? You should be working. Say again. Ah, you got your computer. Did you have it? Oh, you were in a different class? Okay. I've had a few people moving, so I understand. Where is... Here we go. There's the code. No. I might keep the squads the same as far as who's in them, but you'll swap out leadership roles.
Actually, I'm gonna miss the chair.
Why aren't you working?
Okay, because I
Shh. What? Yep, use the slideshow and the other document that I put in there. This. Do you have the code? You good? All right. So in this one, you use this one because on the paper the spectrographs don't really show up very well, right? Because it's black and white and kind of the copier is not great. The questions? This one? This one? Heavier elements. Yeah. Yeah, you're given the right answer. You just have to recognize it. Yeah, it's review. You guys, you're reviewing for the quiz tomorrow. This will help you prepare. I'd even like to give you credit for it, like engagement points, if you came to class with it finished.
You want to hit the button on this?
Oh, yes, please. Thank you.